Hey, Astronomy 152, welcome to Astronomy in our new semester anyway. I wanted to post this lecture so we could kind of start talking about the different parts of the sun and that we could get the different parts of the sun as being part of our lingo and the language that we use. At any rate, so today I wanted to start off with talking about the different layers of the sun and their different, what's the process that's going on in that layer, as well as perhaps the temperature and some other things. What's the name of it? And in order to make this easier for hopefully you to understand, I'm going to compare it to a pot of boiling water on a stove top. Okay, so if you consider a pot of boiling water on the stove top, the first thing you come to is the source of the heat, right? And on as far as the source of the heat goes, on a stove top it could be a convection or a metal piece, which is like using current and getting heated up because current, or it could be because it's a gas flame. Right, and you have a gas fire. At any rate, you have a source, and that's at the beginning. Okay, the source of the sun's power comes from what's known as the core. In the core, hydrogen plus hydrogen yields helium. Now, we're going to talk more about this reaction in a further episode, and of course you guys should realize that will probably end up, you'll have to talk about this reaction as part of one of your discussion questions eventually, okay? But for right now, we're just going to say that in the core of the sun you have nuclear fusion, and that's the source of the heat of the sun, and that this happens at somewhere around 15 million Kelvin. Now, we could talk about unit conversions all we want to, but 15 million Kelvin, 15 million Celsius, they're about the same, and well, it's probably pretty close to 15 million Fahrenheit, whatever Fahrenheit. That's hot, right? Holy moly, that's hot. At any rate, so that's very, very hot. The next thing you come to on the pot of boiling water on the stove top is the pot itself, where you have the metal of the pot, right? And what happens is the heat is transferred from the bottom of the pot to the top of the bottom of the pot through what's known as a radiative process. In other words, light continuously gets absorbed and then re-emitted, and then absorbed and then re-emitted. And as you can see from this here, the light kind of makes this weird, it doesn't know where it's going. Sometimes it goes towards the surface, sometimes it doesn't. Sometimes it goes back towards the middle, sometimes it goes that way. You could go anywhere, it could go in random directions. The point being is that the light is continuously being absorbed and then re-emitted and then reabsorbed and then re-emitted in what's known as a radiative process. Okay, and so that comes to our next layer of the sun, known as the radiative zone. Okay, this one, and you may want to look in your book for the actual numbers here, but this one I'm going to say is around 3.5 million Kelvin. At any rate, there's a range, a temperature range, and so you may want to actually look into that in your book. But at any rate, we have the radiative zone. All right. Now the next thing you come to is the water itself, right? And what's happening in the water is that the hot water is rising to the surface and the cooler water is falling towards the bottom of the pot. At any rate, this is what makes a hot air balloon rise, doesn't it? At any rate, the hot air balloon, what happens is you heat up the air inside the balloon, and because hot air wants to rise, it will begin to rise at any rate. So this is known as a convection or a convective process, okay, where cool gases are falling towards the middle of the sun and hot gases are rising to the surface of the sun. This convection zone, and I'm going to give a temperature of about 1.5 million for it. The convection zone is where the heat is constantly circulating like that. And in a very much same way a convection oven works. You know how a convection oven works, of course, which is it's got a fan inside of it to keep the air circulating so that you don't have a hot spot. And if you don't have a convection oven, then you know you can't put your chocolate chip cookies on the top rack of the stove, because the ones in the middle will get burnt and the ones on the outside won't quite be done yet, right? At any rate, a convection oven, the air circulates inside of it through a convection process, and that's of course why it's known as a convection oven. At any rate, we have our convection zone, and we can actually see this convection zone in what is known as granules. At any rate, these are little bubbles inside the surface of the sun. I say little, but that's really not very clever of me, because the bubbles are all about the size of Earth. Anyway, that's not a very little bubble, is it? All right, the next thing you come to is the surface of the water itself. All right, and that is that surface here on the sun is called the photosphere. Now, of course, photo means light, okay, and so the photosphere is where the sun actually emits light and lets it escape out to the rest of the universe. All right, so we have the photosphere. Now this photosphere is only 6,000 degrees Kelvin. Of course, if you look it up, it's 5,600 degrees Fahrenheit or Kelvin. At any rate, we'll worry about that later on in topic 2, stars. But for right now, we'll just say it's about 6,000. But at any rate, the visible surface of the sun is called the photosphere. All right. Now, here's the weird part, which is we got the steam rising up off of the pot of boiling water, right? And which one's actually hotter, the steam or the boiling water? And well, the answer is, of course, the steam is actually hotter. Okay, now if you stick your hand in the steam, it won't burn it. If you stick your hand in the boiling pot, it will burn it. And I wonder why that is. If the steam is actually hotter, then how come it doesn't burn your hand? That's a discussion question. I wonder if you can answer that. See if you can. Post a reply to me on why steam, even though it's hotter, doesn't burn like the pot of boiling water does. All right, but at any rate, steam is actually hotter than boiling water. Okay, and so the reason I make that point is this steam rising up off the pot, the atmosphere of the sun is actually hotter than the photosphere of the sun. You notice we got all the way down to 6,000. We were in the millions before, but we've gotten all the way down to 6,000. And well, now we're going to start talking about the atmosphere of the sun. And really, there are 2 types of atmospheres that we want to talk about. There's a transition zone, which the book mentions, but really for us, we only want to talk about these 2 zones because they have names that we can remember. So the atmosphere, how do you say color in Latin? Anyway, chroma, all right, chromo or chroma. You may have actually seen an adjustment on your TV set for chroma, where you can adjust the color of your TV set using the chroma adjustment. All right. At any rate, the chromosphere is the lower atmosphere of the sun, and it went back up to about a million degrees. All right. And well, the higher atmosphere of the sun, the upper atmosphere of the sun, is, I'm just going to say it's around 1,000,000 degrees too. It's very hot. And of course, what's its name anyway? The name of the upper atmosphere. Okay, so Maddie hit the wrong button and stopped the thing. Anyway, poor Maddie, she got to come to class. But So anyway, we're almost done, and the last layer of the solar or the sun that we want to talk about is known as the corona. Of course, Mexican for beer, right? At any rate, corona is the upper atmosphere of the sun. Now, these two, the chromosphere and the corona, you've never seen them before. They are bright and they all do give off color, but they're overpowered by the sun itself and by the photosphere. You've probably never seen the chromosphere or corona unless you happen to remember August 21st, 2017, which was the solar eclipse day. Okay, on that day, during the full total solar eclipse, you could, for me in Spartanburg, I got to view the corona for I think about 2 minutes during the solar eclipse before well, no, I could see it before, but anyway, you don't get to see it for long, and the only time you get to see it is during a solar eclipse. All right, but at any rate, he's the upper atmosphere of the sun. Now, the other things that I want to talk about here, just kind of real quickly, is you can have sunspots. Sunspots would be just dark regions on the sun. Instead of being 6,000 degrees, they're like 4,000 degrees. They're still hot as heck, and my numbers were just made up there. But they're cooler regions on the surface of the sun, and that's why they're called a sunspot. All right. You can have solar flares, which are going to be little eruptions on the surface of the sun. You can have solar prominences, which would be like big filaments of sun that are big plumes of gas that are jutting out into space, and you might see those with the solar telescope. At any rate, and then the last but not least, these giant clouds of gas that escape from the sun and drift out into space, and I'm missing the word for it right now. Coronal mass ejection. At any rate, sometimes they abbreviate it as a CME. These coronal mass ejections are huge plumes of ionized gas. If they get aimed at Earth when they blow off the sun, it can actually cause significant damage to our electrical infrastructure. That's why there's a whole system of science based on which tries to predict when these solar storms are going to happen and when they're going to be aimed at Earth, so that maybe we could be ready for them. At any rate, it's called a coronal mass ejection. At any rate, those are the things that are associated with the sun, and hopefully out of all that you found something that you would like to do a solar presentation on, because of course that's what we're doing this week in astronomy, is we're going to be doing a solar presentation. All right, well, good luck to you. We'll see you soon.